All right, so here we go. So we're going to learn today about Newton's third law and how to deal with systems of objects. I think most of the examples, or I know all of the examples in this, are objects that are being pushed, which is a fairly arbitrary way for me to have split up this chapter, but if I hadn't, then your homework assignment would have been way too long. So most of this is going to be review. Really, the last example, I think, is going to be the only thing that's brand new. But I think there's some value in going through some review. All right, so I'm going to kind of run through some basics and through two examples real fast, and then I'll definitely focus more on the last example, okay? So here we go. All right, so quick reminder, these are honestly just the honors notes from last year's. So remember, every force in the entire universe has two objects associated with it, all right? There's the object being pushed or pulled. When you make your free body diagram, that's the object you draw, right? So like a box, that's the object being pushed or pulled, all right? And then the second object is the object doing the pushing or pulling, like Roy pushes the box, right? So it is super, 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 super important that you identify both of those objects, okay? So in this example, this force here is an interaction between Roy and the box. Okay, Roy pushes box, two objects, Roy, box. All right, so Newton's third law, hopefully you remember, says for every action force, there is an equal and opposite reaction force. If Roy pushes the box with some amount of force, then the box is going to push Roy with the same amount of force. All right, here that is summarized here. If object A pushes or pulls object B, then object B will push or pull object A with an equal amount of force, but in the opposite direction. Okay, so if your action force is object A pushes object B forward, then your reaction is object B pushes object A backward. All right, so I guess the notation that I would probably use here is the force of object A pushing object B, and I would call this the force of object B pushing object A. And so Newton's third law says those forces are equal and opposite. Okay? All right, important things to notice. If your action is a push, your reaction is a push. If your action is a pull, your reaction is a pull. Remember, the action and reaction occurs simultaneously. As long as object A pushes object B pushes object A. This is not cause and effect, okay? It's not first A pushes B, then B pushes A. They occur simultaneously. Remember that which action is the action, or which force is the action, and which one's the reaction is totally arbitrary. Remember that they're always equal, the action and reaction forces, and remember that they never cancel, right? So in the drawing I had before, we had our box with the force of Roy, right? The reaction would be the force of the box pushing Roy. Okay, and those forces don't cancel because the force of Roy acts on the box, and the force of the box acts on Roy. Those forces can't cancel because they act on different objects. Okay, so that is a quick, I don't know how many minutes we are in here, but a couple minute review. All right. So here's just a bunch of examples. I don't know that we need to run through all these. If Carl pushes the box pushes Carl, blah, 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 blah. Probably the one thing that I do want to make sure that I talk about is this one. A ball falls off a roof. The reason the ball is falling is because of gravity. Okay, so the way that you need to think about that is if this is your ball, remember, we got to identify the force of gravity to an object. It's actually the force of the Earth's gravity. So we replace force of gravity with the force of the Earth pulling the ball, right? And then the reaction is, technically, it's the ball's gravity pulling the Earth up, okay? And so that's the force of the ball pulling the Earth. And those two forces are equal. The reason that we only notice the ball moving is because the ball has a small mass and a large acceleration, whereas the Earth has a giant mass and a teeny little acceleration. Okay. All right. So this is all kind of more of the same. Keep in mind, like when you walk, what are you doing? You're pushing the ground backwards, right? And the reaction is the ground pushes you forward. Okay? So if this doesn't look familiar to you, please go back and rewatch the honors videos because these examples are all in there in more detail. All right, now this is huge, this chapter. As I was going through and writing up my examples and solving the homework problems for this chapter, something that I was very conscious of is sort of how to help you guys navigate your way through the signs. Okay, so what happens is, as you've noticed, in AP, a lot of times we don't have numbers, right? So we have to make our free body diagrams with variables, right? Okay, so suppose I've got a scenario in which, you know, let's just go back to what we were just talking about. So Roy is pushing a box, okay? So there's this force that is sort of a mutual interaction between Roy and the box, right? In other words, there's the force of Roy pushing the box, and then there's the reaction of the force of the box pushing Roy, right? Now, ordinarily, what I would do is I would, well, maybe I'm getting ahead of myself. All right, so these two forces are equal, right? So let's give them a name, okay? These two forces are equal. So let's call both of these forces, I don't know, let's call them F, all right? It doesn't really matter. So this force is F, and this force is F, right? Now, ordinarily, what I would do is, like, suppose we were trying to find F, and we were looking at the free body diagram for just Roy. Ordinarily, what I would do is I'd say solve for it, and if F turns out to be negative, then you know that it points to the left. This chapter, I'm not going to do that, all right? When you've got a system like this, the problem is both of these forces can't be F, right? Because if this is F, this is actually equal to negative F, isn't it? Okay, so I will, when you're using the same symbol, in this case F, to represent a force on two different objects, I will always assume that the value of that force is positive, okay? And then if direction indicates that it's negative, like this, then I'll manufacture a negative sign by putting a negative in front of it. And that's just indicating that this is some value F, and this is the same thing but opposite, okay? Now, if I solve the problem and I solve for F and I get a negative, then that just tells me that my direction's flip-flopped, right? Okay, so this is one of the rare times where I'm going to encourage you to sort of manufacture those negative signs by putting them in there, all right? And I'll try to make sure I call attention to that as I go through the examples. So if you didn't quite follow that, we'll get there, okay? All right, so let's do an example here. So it says Mr. Hecker, who has a mass of 75 kilograms, stands on a perfectly frictionless skateboard and uses a force of 450 newtons to push a 150 kilogram filing cabinet. It's big enough so you can see it a little bit better. A 150 kilogram filing cabinet that sits on the floor. Make a separate free body diagram for any important object in this exchange. Okay, so the problem is about me pushing the filing cabinet, right? So let's think about that. So here's the filing cabinet. Here it is a 150 kilogram cabinet. So to make my free body diagram, you start with your force of gravity. 150 times 9.8 gives you negative 1470. It's just sitting on a floor. So there's a normal force. All right, so maybe I'm over here pushing it. So then there's going to be the force of Hecker pushing this way with a force of 450 newtons, right? All right, now, presumably, the filing cabinet's not going to move. And to be honest, I really probably should have written this example a little bit more clearly. But so if the floor is frictionless, then we're done, right? And so the net force on my cabinet would just be 450. So you can find your acceleration, right? 450 over 150, you get an acceleration of 3. More likely, it's not going to move, right? Because filing cabinets are usually pretty heavy. And so there's probably a pretty significant amount of friction here, right? So let's assume that there is, in fact, friction. So here's our force of friction. It would be static, I guess, if it's not moving, right? Again, I'm assuming I should have written the example better, but conceptually. All right, so if it's not moving, then the static friction must be at least 450, or I guess exactly 450. The max is at least 450. And there we go, it doesn't move, right? So then over here, so we're going to have acceleration 0 and net force is 0. Again, assuming that the cabinet doesn't move, okay? So there we go. All right, now, meanwhile, if you look at me, here's me, right? So this is my action force. It's the force of Hecker pushing the cabinet, right? The reaction is going to be the force of the cabinet pushing me, right? So let's draw that. Force of cabinet is going to be negative 450 newtons, right? Okay. And that force is in fact negative because it's to the left. And let's see, we know that my mass is 75 kilograms, so we can figure out the force of gravity. Oh, I need different variables. This is force of gravity on the cabinet, normal force on cabinet. This is the force of gravity on Hecker, right? They're different things, right? So what's this give you? Negative 735 newtons. And, uh-oh, I did not do a good job budgeting my space. There's a normal force here of positive 735 newtons. Now, for me, it says I'm on a frictionless skateboard. So now there's no friction, which means the net force for me is going to be negative 450 newtons. So you can now find the acceleration, right? 450 over 75, and it gives you negative 6 meters per second squared. Okay, so that's that. All right, so again, though, worth noting that these two forces that I have highlighted in yellow, although they are equal and opposite, they do not cancel because one of them acts on me, is for Hecker, and the other one acts on the cabinet. All right, the only forces that cancel are forces that act on the same object. So if you wanted to identify forces that cancel, then that would be this force and this force cancel. And similarly, this force and this force cancel, all right? But those do not make up action-reaction pairs, right? Okay, so that is that. All right, all right. So, I mean, this was, this was kind of the basic example from last year, right? The ducks on the frozen pond, or not ducks, penguins. Because I'm sure you remember what animals I put in my example last year. All right, so sometimes, though, we need to make a free body diagram for a system. So remember, the system consists of one or more bodies, all right? Whoa, it's not what I want to do. System consists of one or more bodies. Any force on the bodies inside a system exerted by bodies outside the system is what is called an external force, all right? So if you've got a system, a collection of objects, and then an object that is not in that system exerts a force on one of the objects in the system, that is called an external force, okay? The net force on a system is defined as the sum of all of the external forces. Notice you don't need to worry about forces exerted by objects inside the system because those are called internal forces, all right? So if my system is objects A and B, and in the problem A pushes B, that does not affect the net force on the AB system, okay? So when you make a free body diagram for a system, you do not include the internal forces, all right? When you make a free body diagram for a system, you do not include the internal forces, all right? Last year I kept saying you can't sit inside your car and push on the dashboard and make it go, right? Because you're an internal force. If you push the car is going to push you. All of that sort of contained within the system, and it doesn't affect the overall motion, okay? So what this means is when you do these problems that have systems, remember there are a number of different free body diagrams you can draw. You can make a free body diagram for the system as a whole or for the individual bodies within the system, all right? And they're different, okay? So with that in mind, let's run through this first example, all right? So in this example, we've got a 40-kilogram box of kittens sitting in the center of a frictionless warehouse. All right, Roy needs to move the box of kittens, but unfortunately he's allergic to kittens. So he finds a 120-kilogram crate full of peanuts, which he thankfully is not allergic to, and he uses the box of peanuts to push the kittens. He pushes the peanuts with a force of 480 newtons. Okay, so we need to make free body diagrams. All right, so what I encouraged you guys to do last year was to start with the system, okay? So let's do that. I'm actually going to do these out of order, all right? So we're going to do the peanut kitten system, all right? So if we do that, let's see. So we've got a box of kittens, right? So here's our kittens, 40 kilograms, right? Roy wants to push them, but he can't. So let's assume he wants to push them to the right, okay? He can't push the kittens directly, so he takes this larger 120-kilogram box of peanuts, and he pushes them, right? Okay, so in this problem, here is my system. All right, And now there is an external force from Roy. He's pushing with a force of 480 newtons. Let's see. It's a frictionless warehouse, so I don't need to worry about friction, right? All right, and then gravity is going to pull this whole thing down, right? So our force of gravity is going to be 160, right? Because that's our total mass, right? Because 120 plus 40 is 160. So that gives you negative 1576 newtons. Sorry, that's wrong. 1568. Somehow I forgot to write out this example before I started here. Oops. There we go. All right, which means that there must be a normal force, right? Because the kittens and the peanuts are not, in fact, falling through the floor. So there's our free body diagram for the peanut kitten system. So we can now find our net force. It's just going to be 480, right? Because the only force coming from outside of the system is Roy. Well, other than gravity and normal force, but those cancel. And so we can find our acceleration, right? Just by doing net force over mass. And hopefully you see you get 3 meters per second squared. Okay. Notice in this interaction, I sort of glossed over this. The peanuts are definitely pushing the kittens, right? But that is an internal force because it's a force from the peanuts, which is part of our system. Similarly, the kittens are pushing the peanuts backwards, but again, internal force, okay? So we don't need to worry about that. All right, so that is that. All right, now let's do this. Oh, I don't like that it did that. It didn't shrink the highlighting for some reason. All right, so now let's do the peanuts, all right? Oh, shoot. So this was peanuts, this was kittens, right? Okay. I guess it doesn't really matter which object you start with here, whether you do the peanuts or the kittens next. I think I'm actually going to do the kittens first, because there are less forces on the kittens, right? All right, so let's do that next. So here we go. Kittens. Kittens. Okay, so here we go. So here is our, well, we'll do this in a different color. How about that? So here's the kittens. Kittens, you got to make sound effects. What was the mass of the kittens? 40 kilograms. So let's see, our force of gravity is negative 392 newtons. They don't move down because they're sitting on the floor of the warehouse. So there's a normal force from the floor, which is positive 392 newtons. I guess I should give this a different name, right? Now I've got 2 normal forces. So this is the normal force on the kittens and the force of gravity on the kittens. I probably, over here, should have called this system and system to be specific. All right, let's see. Now, what moves the kittens forwards? Roy? Nope, because Roy pushes the peanuts, right? Remember, Roy was allergic to the kittens, so Roy does not touch the kittens. The only thing touching the kittens is the peanuts. Okay, so there's this peanut force, this peanut-kitten interaction, and here we've got the peanuts pushing the kitten. All right, but what we know already is we know their acceleration, right? We just found it over here. It's 3 meters per second squared, right? And so that means we can do net force equals net force, right? Net force equals net force. So the mass of the kittens times acceleration of the kittens ought to be equal to the force from the peanuts. So let's see. So 40 times 3 equals the force of the peanuts. It's 120 newtons. So there we go, 120 newtons. Okay, so there is the free body diagram for the kittens. Goes over there, all right? So I guess the last thing we need to do is the peanuts, right? So this is, I don't know if you guys remember this, by the time you got to your third free body diagram, you were able to check it and see if it was right. Okay, so that's exactly what I'm going to do. Okay, so for the peanuts, there are 2 choices. You can either assume that the force that you found here, oh, that's terrible. Sorry. You can assume that the force that you found here is correct and recalculate your acceleration, or you can assume that the acceleration is correct and recalculate the force of the interaction between the peanuts and the kittens. All right? So what I'm going to do is this. I'm going to assume that the acceleration is right and recalculate the force between the peanuts and the kittens to make sure that we validate Newton's third law, right? Okay? So here we go. So here are the peanuts. They have a mass of 120 kilograms. Gravity is going to pull these guys down with a force of negative 1176. There's got to be a normal force of positive 1176. Try that again. I apparently can't write. 11, oh my glob. 1176 newtons, right? I need to give these a new name. This is the normal force on the peanuts, and the force of gravity on the peanuts. All right, what pushes the peanuts forward? Roy does. And we know that his force is 480 newtons, right? That was given to you in the problem. But since the peanuts are pushing the kittens, that means the kittens are pushing the peanuts. Okay? So, ideally, when we are done, hopefully, this force should equal this force. Okay? So, we can do net force equals net force, right? So the net force on the on the peanuts should equal the net force on the peanuts. So the mass of the peanuts times the acceleration of the peanuts ought to equal the force of Roy. Okay, so maybe here's an example where this is what I was talking about. So we know that these signs are going to be ugly. All right, I'm going to call this negative FK, right? So this will be minus FK, right? Technically plus negative FK. Because our goal is we want the FK to equal FP. And their magnitude is the same, the direction is different, right? So, all right, so anyway, so let's solve this thing. So our mass is 120, our acceleration is 3, force of Roy is 480, minus the force from the kittens, right? So solve it, and you discover that the force of the kittens is, in fact, as we would hope, 120 newtons. Okay? And we're happy because it is, in fact, the same as what we got over here. All right, so that is that. So we got to muscle through. Here we go. Now, we're going to do the same example again, but this time, and this is new, we've never done this before. This time, instead of putting the boxes next to each other, we are stacking them. Okay? So this time, the 40 kilogram box of peanuts is somehow on top of the peanuts. All right? And so question number 1 wants us to find what is the, it's supposed to say maximum force. What is the maximum force you could apply to the peanuts without the kittens sliding off of the peanuts? Okay, so here's the idea. So you've got, here's your peanuts, 120 kilograms. And then you got a 40 kilogram box of kittens on top of it. I don't know why I think this is so funny. All right, and so Roy is going to push over here with some amount of force, right? But the problem is, if he pushes too, whoa, that's not what I wanted to do. All right, so the problem is, if Roy pushes too fast, then the peanuts will move out from under the kittens, and the kittens will fall, and then we'll be sad, because kittens are cute. All right, so what we need to do is we need to figure out what's the maximum force he could apply to the peanuts without the kittens slipping off. All right, so here, we can't start with the system this time, right? Because if we start with the system, we're assuming everything moves together, and it might not move together, right? So this time, rather than starting with the whole system, I'm going to start with the individual objects. Okay? So let's do this. Let's start with the kittens. So let's think about our kittens. The kittens are here. They got a mass of 40 kilograms. So you've got your force of gravity. It's going to be negative 392 newtons. You're going to have your normal force. It's going to be positive 392 newtons. All right, now, if the kittens move, what's moving them? Well, before we had the peanuts kind of over here pushing forwards, right? But we don't anymore. Now the peanuts are underneath, right? And so the goal is we want the kittens to not slide off, which means if they don't slide off, the thing pushing them forwards is friction, right? And even though the kittens are moving, it's still static friction, right? Because the goal is to have them not slide. So remember, the distinction between static and kinetic friction is not moving versus not moving. It's sliding versus not sliding, okay? And in this instance, the goal is to have the kittens not slide, and that not sliding will be achieved by static friction, okay? So it's probably worth our while to go over here and figure out what our maximum static friction is, right? So that's our coefficient of static friction times our normal force. So our coefficient of static friction is 0.4. Our normal force is 392. Multiply, and you get a number that I've written on this piece of paper over here that you can't see. There it is. It is 156.8 newtons. And while we're at it, we might as well find our kinetic friction because it seems like that might be a thing we need later. So you're just going to use 0.3 instead of 0.4. So if you find that, you end up getting 117.6 newtons. Okay? All right, so let's do this. This is all valuable information. Whoa! It's not at all what I wanted to happen. We're going to put that there. Get rid of all this. We're going to take this stuff and shrinkify it. Gonna make sound effect. There's that. All right, cool. All right, so the question is, what's the maximum, again, remember this was supposed to say maximum force that Roy can apply to the peanuts without them slipping. So maximum force would produce maximum acceleration. Maximum acceleration, the kittens, would be applied by the maximum static friction, which is 156.8 newtons. Aha, so now I can calculate the acceleration, right? So I'm just going to do net force on the kittens equals the net force on the kittens. So the mass of the kittens is 40 kilograms. The acceleration of the kittens, don't know. That's equal to our net force. Our net force is just that static friction maximum, right? That's the most force that could possibly push the kittens forwards. So solve it, divide both sides by 40, and you get 3.92 meters per second squared, right? So that's kind of our maximum acceleration that we could get, right? All right, so that is the biggest possible acceleration that I can give the kittens without them slipping off of the peanuts. So now, what does Roy have to do to make that happen? Well, so I guess there's a couple of ways you can do this. Option one is you can look at the system as a whole, which honestly is probably the easier way to do it. Or you can look at just the peanuts. All right, so let's see. So let's look at the system as a whole. I'll do it both ways. All right. So here's the whole system. Here's the peanuts and the kittens. That's 160 kilograms. So the force of gravity on those guys is, what did we decide it was? Negative 1568, I hope. Yeah, 1568. Okay. And so there's a normal force of positive 1568. I'm being sloppy with my units, or my names. I'm reusing my normal force. All right, so there's our normal force. Oh, right, okay, so friction. So the friction actually occurs between the two objects, right? This friction force here is actually the static friction between the peanuts and the kittens, right? So that's an internal force. I don't need to worry about it. Okay? The floor, however, is still frictionless, right? Remember, frictionless warehouse. Okay, so we don't need to worry about that friction down there. Okay, so the only force horizontally on this thing is the force of Roy, right? And so we want to find out, what does Roy's force have to be to get this acceleration? So it's just net force equals net force. So the mass of the system times the maximum acceleration is equal to my net force, which is just Roy's force, right? So solve it, and Roy's force is whatever 160 times 3.92 is. It does end up happening to be 627.2 newtons. Okay? So that's what's going on with the system as a whole. The question then is, let's check it. What does this look like just from the vantage point of the kittens? So let's see if we can do this. Oh, darn it. Darn it. All right. Well, whatever. We're going to shrink our drawings more. Okay. So that was Roy's force. Okay. So now let's look at it from the kittens. All right. So here's our kittens. No. Peanuts. So here's the peanuts. 120 kilograms. Gravity is negative 1176 newtons. Normal force is 1176 newtons. There's a forward force from Roy. I guess that's what we're trying to figure out, so we'll figure that out. Now, what's working against the forward motion? All right, well, so here's the weird bit. And unfortunately, I just shrunk this. All right, but... all right. Okay, so hopefully you did not shrink on your paper. So the idea is, what we figured out before was that the force of friction static between the peanuts and the kittens at its maximum was 156.8 newtons, right? So the idea is what pushed the kittens forward was the friction from the peanuts. In other words, the peanuts are pushing the kittens forward. Well, that means the kittens are pushing the peanuts backwards with a force of negative 156.8 newtons, right? Okay, so now let's find the force of Roy and see what happens. Hopefully, fingers crossed, we'll get the same answer. So here we go. For the peanuts, net force, oh, I wanted that to be blue. Net force equals net force. So let's see, the mass of the peanuts is 120. Acceleration is 3.92. That's got to equal the force of Roy minus that static friction over there. And solve it. And lo and behold, you get 627.2 newtons, just like we did before, up here. Okay? So, there's a lot going on there. All right? So, that means the maximum force he can exert and still have the peanuts and the kittens move together is 627 newtons. Okay? So, let's do this. Bam! So, this, for part A, we decided that was, what was it, 627.2 newtons? All right, so question 2 says what would happen here if you pushed with 560 newtons? Well, the kittens and the peanuts would move together, but your static friction would end up being less than the max, right? Because you wouldn't need as much force to prevent the object from sliding, right? So, you know what? I'm going to let you guys do this one on your own. It's actually very similar to what we just did. So here's the answers. What we end up finding is the Freebody diagram for the kittens on the top looks like this. Your force of static friction ends up being 140 newtons. So then you've got your gravity and your normal force. And then for your peanuts, you're going to have the force of Roy, which is 560 newtons. And your force of kinetic friction is negative 140. And then again, gravity and normal force. Okay? So that's the deal with number 2. All right? They'll move together, nothing weird there. All right? Because they're both going to have the same acceleration, right? The acceleration here ends up being, 3.5 meters a second squared for both objects, right? Okay, now what if he pushes with more than this 627, right? So that's question C. So, well, we already know it's going to slide, right? So then what you do is this. For number 3, you have to draw your objects separate, right? Because now they're no longer moving as a system. And maybe this is a thing that I should have said, is that when you define a system, you don't have to, but usually you define your system as one or more bodies with the same acceleration. I guess that's not always true. In fact, no, or it's not going to be. But for purposes of this chapter, that's a good idea, all right? So, all right, so here we go. So I'm going to start arbitrarily with, which one's on the bottom? The peanuts, right? All right, so here's the force for Roy, 800 newtons. We know they're going to slide across each other, right? So your peanuts, or your kittens, are going to be up here. And the peanuts are going to slide forward under them, which means the friction is going to push them backwards. And its kinetic friction, which we had figured out before, was negative 117.6. Right? And so now the idea is, we know our mass was 120. You're going to have your gravity and your normal force. Those all cancel. So you do net force equals net force, where your net force is this minus that, divided by your mass of 120 kilograms. And you find that the acceleration of the peanuts is 5.69 meters per second squared. Okay? Now, if we find the acceleration of the kittens, we end up getting a different number, which is the whole point. Okay, so now here's the kittens. So the idea is the peanuts are going to be sliding forward under the kittens. So there's some relative motion here, but the idea is the peanuts are trying to drag the kittens forward. Okay, so there's kinetic friction between the peanuts and the kittens, and again, it's 117.6 newtons, right? And you got your gravity and your normal force, but there's nothing pushing the kittens backwards. It's just that there's not enough pushing them forwards. So now, if we do net force equals net force, our net force is just the kinetic friction. Our mass is 40 kilograms. So if you find your acceleration, 117.6 divided by 40, you only get 2.94 meters per second squared. In other words, this acceleration, the acceleration the kittens experience, is less than the acceleration of the peanuts, and so there's the problem, and that's why the peanuts, or the kittens, are going to fall off the peanuts. Okay? A lot of stuff to keep track of here. Okay? I think the big thing to notice in this last example is that because your objects are moving with different accelerations, there's not a lot of practical value in treating the peanut-kitten system as one system. You really need to treat them separately. Okay? All right, this video is a kick in the teeth. I think that the other videos will be a little bit shorter this chapter. Cool.